We've previously set up a framework which allows us to test hypotheses involving single coefficients. So for example, if our regression model was as follows, yt equals beta 1 plus beta 2 x2t plus beta 3 x3t plus ut, if this is our regression model, then the framework that we've developed so far that uses the t-test, either through the confidence interval approach or through the construction of t-test statistics, this allows us to test hypotheses separately about each of the coefficients. So for example, we could test the null hypothesis that the true value of beta 2 is 0 against a two-sided alternative that it's not 0. Or we could test the null hypothesis that the true value of beta 3 is 0 against a two-sided alternative that it's not 0, and so on. Now this is all very well, but what if we wanted to test a multiple hypothesis? In other words, a hypothesis that involved more than one parameter at the same time. So for example, suppose I was interested in testing a joint null hypothesis that the value of beta 2 is 0 and the value of beta 3 is 0 at the same time. Well, we couldn't do that using the framework that we've developed so far. We need a much more general framework than that. And the framework that we use is based on the F-test. So in this more general framework, it's going to no longer be possible to be able to examine individual coefficients and their standard errors as a way to construct hypothesis tests. We need some measure instead which looks at the regression model as a whole. And this measure that we use is focused upon the residual sum of squares. So essentially, what we do when we conduct multiple hypothesis tests using the F-testing framework is to estimate two regressions. We estimate an unrestricted regression where ordinary least squares is allowed to completely freely determine the values of all of the parameters in the way that it wants to. So this is the regression model that we've developed before. And we also estimate a second regression, which we call the restricted regression. So what we do is we take our values under the null hypothesis and impose those on the model, rearrange it if necessary, and then estimate a restricted model where the restrictions are already imposed upon the model so that they're going to be present. Now, if we think back to what ordinary least squares does, ordinary least squares chooses the parameter values that minimize the residual sum of squares, i.e. that best fit the data. The question we then ask when we develop the F-testing framework is, when we impose the restriction, to what extent does the residual sum of squares change? Now we can be a bit more specific than that. We know that ordinary least squares minimises the residual sum of squares with respect to the parameter values that it chooses. When we estimate a restricted model, therefore, we would expect the residual sum of squares to rise. So the question that we ask when we test F-tests and we use this framework to test hypotheses that we're interested in involving more than one parameter, the approach that we adopt says essentially, how much does the residual sum of squares increase when we impose the restrictions on the model? In very general terms, if the residual sum of squares only increases very slightly, we say that the restrictions are supported by the data. That is, the fit of the model after imposing the restrictions isn't very much worse than it was when we started. If, on the other hand, the residual sum of squares increases substantially when we impose the restrictions, then we say that the model has kind of extracted a large penalty in terms of the residual sum of squares when we impose the restrictions on that model. Therefore, we'd say in that case that the restrictions are not supported by the data. So all we do is to say, how much does the residual sum of squares go up when we include the restrictions and estimate the restricted model. So the formulation of the F-test statistic embodies the residual sum of squares from the restricted and unrestricted regressions and the difference between these two. We denote the residual sum of squares from the restricted regression by RRSS and the residual sum of squares from the unrestricted regression by URSS. So we can see that in the numerator of the formula for calculating the statistic, we have the difference between the two residual sums of squares. We then divide by or normalise by the unrestricted residual sum of squares, which kind of removes the scaling, if you like. We then multiply by t minus k divided by m. Now we know what t is, we've already met that. T is the number of observations that we've got in our sample. We've also met k before. K is the number of regressors including a constant, or the number of parameters that we estimate. Now in the context of F-tests, we need to be slightly more precise than this about our definition of k. More specifically in this case, we need to say that k is the number of regressors including the constant term, or the number of parameters that we're estimating in the unrestricted regression model. Because it turns out that in this case, there will be fewer parameters to estimate in the restricted model than in the unrestricted model. And we'll see why that is the case later on. Finally, the last element in the formula is m, which is the number of restrictions that are present under the null hypothesis, or that we're imposing on the model. We'll get some examples in a minute about the F-test statistic and what values of m the test statistic takes on in each of these cases. This is the way that we calculate the F-test statistic. Now, an obvious question is, which will be bigger, the restricted residual sum of squares or the unrestricted residual sum of squares? Well, strictly speaking, we can write restricted residual sum of squares is always at least as big, or is greater than or equal to unrestricted residual sum of squares. Now, once again, we know that from the way that we've set up the model. We know that ordinary least squares chooses the parameter values that best fit the data, that minimize the residual sum of squares. Obviously, if by imposing some restrictions like this onto the model, if we could have got a lower residual sum of squares from doing that, then ordinary least squares would have done that in the first place automatically. To give you an illustration of that, suppose, for example, that you have to make a journey, let's say, between Reading and London. Now, if you were left to your own devices and you were travelling by car, you'd probably travel along the M4, which is a direct route from Reading to London. If I then impose some restrictions on your journey, so for example I said that your journey from Reading to London had to go via Oxford, then it couldn't possibly be the case that you could get to London more quickly going via Oxford than you could have done if you were allowed to completely freely determine the way that you could go. If you could get to London quicker via Oxford than if you went directly from Reading to London, then you would have chosen to go via Oxford in the first place. Similarly, if ordinary least squares could have found a lower residual sum of squares by imposing the parameter restrictions here onto the model, then it would have done that automatically. So therefore, it must be the case that when we impose some restrictions, we get a kind of less desirable outcome. In other words, we get a higher residual sum of squares. Now, obviously, this is an inequality here, and there could be situations where the restricted residual sums of squares exactly equaled the unrestricted residual sum of squares. Under what circumstances would that be the case? Well, that would only be the case if, by imposing the restrictions, we end up with a residual sum of squares that is identical for the restricted and unrestricted models. How could that be the case? Well, that could only be the case if the restriction was already present in the data automatically, and therefore imposing the restriction wasn't really imposing any restriction at all. So in this context, if we were testing the null hypothesis that the true value of beta 2 is 0 and the true value of beta 3 is 0, this restricted residual sum of squares and unrestricted residual sum of squares would only be the same if our estimated value of beta 2 hat and beta 3 hat were both exactly equal to 0. Obviously, that's extremely unlikely to actually happen in practice. Even if the true values of beta 2 and beta 3 were 0, when we estimate a regression model, we're never going to get estimated coefficients that are exactly 0. So therefore, in any practical context, the restricted residual sum of squares will always be bigger than the unrestricted residual sum of squares. Now, we know what the format of the F-test statistic is. An obvious question then to ask is, what is the distribution of the F-test statistic? Well, it turns out that the F-test statistic follows an F distribution. Now, the difference between the F and the T distributions is that the T distribution had only one parameter, that is the degrees of freedom, which described the shape of that distribution. We also know that the T distribution, like the normal distribution, is symmetrical about its mean value of 0. The F distribution is very different from the T and the normal. The F distribution is asymmetric, that is, it's not symmetrical about any value. And secondly, the F distribution only takes on positive values. So if we were to try and draw a diagram of what the F distribution might look like, then the F distribution might look something a bit like this. So usually it's kind of squashed over to the left-hand side with a kind of long, thin upper tail. Now, one upshot of that is that because the F distribution is asymmetric, we don't look in tables for critical values and apply one critical value to the upper tail of the distribution and the same critical value but taken multiplied by -1, or the negative critical value for the lower tail. When we are looking at the F distribution, we always put the whole of the rejection region in the upper tail. So, for example, if we wanted an alpha equals 5% significance level for this rejection region, then we would put the whole of the rejection region in the upper tail. Now, in the context of F-tests, as we'll see later, that does not mean that we're doing a one-sided test. In fact, with F distribution tests, we're always doing two-sided tests, never one-sided tests. So still, we need to remember that we look up a critical value which will put the whole of the significance level that we want into the same upper rejection region. Now, I said that the T distribution has one degrees of freedom parameter that describes the shape of the distribution. We know that if T minus K increases for a T distributed random variable with T minus K degrees of freedom, then that distribution will be squashed inwards and pulled upwards, so it will become more like a normal distribution. For an F distribution, on the other hand, there are two degrees of freedom parameters rather than one. So there are two separate parameters that describe the shape of the F distribution. And if we vary the values of these degree of freedom parameters, we could end up with an F distribution that moves over to the right. It might become more peaked over here and become squashed inwards and so on. So the degrees of freedom parameters describe the shape that the F distribution takes. Now, the degrees of freedom parameters for the F-test statistics that we're developing here are M and T minus K. So remember, M was the number of restrictions that we imposed in our model, and T minus K was the number of observations minus the number of parameters we're estimating in the unrestricted regression model. So the F distribution has these two degrees of freedom, and unfortunately, an F distribution with M and T minus K degrees of freedom is not the same as an F distribution with T minus K and M degrees of freedom. So when we look up the critical values from the F distribution tables, we need to be careful to ensure that we get the order of the degrees of freedom parameters right. If we look up the distribution with these degree of freedom parameters reversed, we're going to get a very different and very wrong critical value. So we need to make sure we get these things correct. We also know that the critical value that we find in the tables will be in column M and row T minus K of the F distribution tables. And we'll get an example in a few moments that shows us how we actually use the F distribution tables and how we obtain the critical value. But I think you can see from here, once we know what these two things are, it's going to be fairly easy. Now, let's have a look at a quick example that shows us how we estimate the restricted regression model and how we impose the restrictions. So, let's suppose that we have a regression model with 3 explanatory variables plus a constant. In other words, we have 4 parameters to estimate. And let's suppose that we're interested in testing the null hypothesis that the true values of beta 3 plus beta 4 sum to 1. So the null hypothesis that we're testing is that beta 3 plus beta 4 equals 1. Against, obviously, as I said, as is always the case for the F distribution, a two-sided alternative where beta 3 plus beta 4 does not equal 1. So just to make this regression model here correct and corresponding to the example that we've got, we need to add in another explanatory variable here. So what would be the restricted and unrestricted regression models for testing a hypothesis of this form? Well, the unrestricted regression, as always, is the one where we allow ordinary least squares to completely freely determine the values of all of the parameters. Here, this will be the unrestricted regression model, the one that we started with. What about the restricted regression model? How do we actually get an idea of that? Well, what we do is take our restriction implied by the value here under the null hypothesis, rearrange it and substitute it into the model. By substituting the restriction into the model, we're forcing the restriction to be present in that model when we estimate the restricted version of it. So if beta 3 plus beta 4 equals 1, then obviously we could write this as beta 4 equals 1 minus beta 3. We then take this and substitute it into the model. Now, an obvious question you might ask is, well, what would happen if instead of doing that, we wrote beta 3 equals 1 minus beta 4? Well, we'll come back to that point a bit later on, but it turns out that it wouldn't make any difference whatsoever. So let's just make some space here, and what we need to do is to substitute into this regression model 4 beta 4. So what do we get? Well, we have yt equals beta 1 plus beta 2 x 2t plus beta 3 x 3t plus 1 minus beta 3 multiplied by x 4t plus ut. Okay, so now this is already a restricted version of the model, because previously ordinary least squares could choose any value it wanted for this parameter. Now we're saying to ordinary least squares, you have to take 1 minus the parameter value that you chose on this variable x3. So this is already a form of the restricted regression, but it turns out that this isn't yet in a form which we can estimate on a computer. If we tried to tell the computer to estimate this model, it would end up not imposing this restriction at all, but ending up choosing completely freely a value to attach to this variable. So what we now need to do is to rearrange this model slightly to get a form which we can estimate on a computer. So the way that we do things now is to rearrange this, and first of all we expand the parentheses. So what do we get? We have yt equals beta 1 plus beta 2 x 2t plus beta 3 x 3t. Then what have we got? We've got a plus x 4t, and then we've got a minus beta 3 x 4t plus ut. So once again, this is another form of the restricted regression, but it's still not in a form which we could use a computer to estimate. And the problems in terms of computer estimation are twofold. The first thing is that we've now got a variable over here on the right-hand side with no parameter in front of it. How do we deal with that? Well, the answer is any variables on the right-hand side of this restricted model which don't have any parameter attached to them, we then take over to the left-hand side of the regression equation. So yt over here then becomes yt minus x4t. Okay, so we subtract x4t from both sides of the equation. Then obviously we've still got equals beta 1 plus beta 2 x2t. And then what we do is to gather together all of the terms in each of the betas. Now in this case here, the only term that's got where we've got a beta that's involved in more than one term here is beta 3. How many lots of beta 3 have we got? Well, we've got x3 lots of beta 3 from here, and we've got minus x40 lots of beta from over here, and then once again plus ut. So what we've done is factorised here in terms of beta. We're nearly at the end now. All we need to do is to make a substitution into this regression model in order to get the result that we want. So let's create two new variables which we could call whatever we want, but let's create a new variable called pt, which is yt minus x4t, and let's create a new variable called qt, which is x3t minus x4t. Okay, and let's substitute in for yt minus x4t here and for x3t minus x4t over here. Then what do we get? We get our restricted regression that we actually estimate on the computer is a regression of our new variable pt on a constant, the variable x2t, and our new variable that we've created, qt. Okay, so this is the final form of restricted regression which we actually estimate on the computer. And you can see that we've always got one variable multiplied by one parameter here, and this is back to the standard form for the regression model. So this is something that we can estimate. And we could make these substitutions here, either in a piece of spreadsheet software, we could create these new variables, or we could get our econometric computer package also to do that for us instead. Now, once again, just to come back to this question that I raised earlier, I substituted out here for, in here, for beta 4. I could have instead substituted here for beta 3, because under the null hypothesis, we could have written beta 3 equals 1 minus beta 4. And an obvious question to ask is, well, what would have happened if we substituted out beta 3 instead of beta 4? Well, the answer is, if we'd have done that and rearranged the model, we would have ended up with an identical model to estimate at the end, and therefore an identical residual sum of squares and an identical value of the test statistic. So it turns out that it doesn't matter which of these two approaches we use, we'll always get the same answer. So, what I want to do now, before we look at an example, is just to give you some intuition about what the number of restrictions in the model is. So, for example, let's suppose that we wanted to test the second of these two joint null hypotheses, first of all, that the true value of beta 2 is 1 and the true value of beta 3 is minus 1. How many restrictions would that imply? Well, obviously, that would imply 2 restrictions. Very informally, we can say that the number of restrictions we're testing is the same as the number of equal signs that we have under the null hypothesis. Similarly, if we're testing a restriction that the true value of beta 2 is 0, and the true value of beta 3 is 0, and the true value of beta 4 is 0, there are 3 restrictions. What about the first in these lists of null hypotheses that we want to test? In other words, what if we want to test the restriction that the sum of the true values of beta 1 and beta 2 is 2? How many restrictions are there? Well, you might initially have thought, after looking at that there were 2 restrictions. Well, in fact, it turns out that there's only 1 restriction there, which happens to involve more than 1 parameter. So a restriction can involve as many parameters as we want, but if there's only 1 equal sign, we're only testing 1 restriction. Now, if we look at the last of these 3 restrictions, where in fact there are 3 restrictions that we're imposing, that the true value of beta 2 is 0, and the true value of beta 3 is 0, and the true value of beta 4 is 0 at the same time, then in the context of this regression model with 3 explanatory variables plus a constant term, then that's a very special hypothesis. And just as calculating the t-ratios to test individually the null hypothesis that the true value of a parameter is 0 is a special hypothesis that we always want to test, in the context of multiple regressions, then this last restriction is also a special one which we'd always want to test. And this last restriction is one that's tested by what's known as the regression F-test statistic. Now, what does the regression F-test statistic test? Well, the answer is, if we come back to our regression model here, and I try and just tidy it up very slightly, the regression F-test statistic is sometimes called a kind of test for nonsense regressions, or a test for junk regressions. And we'll be able to see why it's sometimes called that by thinking about what's implied by that null hypothesis. So if we're testing a null hypothesis that the true value of beta 2 is 0 and the true value of beta 3 is 0 and the true value of beta 4 is 0, if this null hypothesis were not rejected, then what would that mean about our regression model? Well, that would mean it's plausible that the true but unknown population parameter values for all of the slope coefficients in this model, beta 2, beta 3 and beta 4, these could all plausibly be 0. What happens if all of these values are all 0 at the same time? Well, the answer is if these are all 0 at the same time, then none of the explanatory variables which we've proposed here has any significant explanatory power for the variable that we're trying to explain y. So that being the case, we could essentially remove all of these variables from the regression. And if we do that, what do we end up left with? Well, the answer, we end up just left with an intercept term. No explanatory variables. So you can see why this is a test for junk regressions or nonsense regressions. If we fail to reject this null hypothesis, then that means our model in a sense is completely useless. It's as bad as it could be. We haven't found any variables that significantly explain the dependent variable y when we take them as a whole together. So this is a null hypothesis that we'll always be interested in testing, and it's a null hypothesis which we always want to reject. And computer packages will always calculate the value of the test statistic associated with this null hypothesis for us. Now, it's important to note as well that obviously the restriction implied by this null hypothesis will expand and contract with the number of explanatory variables that we've got in our regression model. If, for example, we had an extra explanatory variable in this regression model, so if I put in here another explanatory variable, so we have multiplied by beta 5 x5t plus ut, okay, then obviously we would have to add one more element to this null hypothesis. So this would be now and beta 5 equals 0. Okay, so you can see, obviously the computer will know how many explanatory variables we're putting into our regression model, and it will expand or contract the size of the null hypothesis that we're testing here accordingly. Note also that we're not interested in testing anything about the value of the intercept parameter here. The intercept here just allows for y to have a non-zero mean, or in other words, it ensures that we don't force the regression line through the origin. So we're not interested in testing anything about beta 1 in this null hypothesis. We're only interested in testing the slope coefficients. Finally, one thing that we need to know is the form of the alternative hypotheses for joint F-tests. Under the null hypothesis here, we had equalities and we had the word and everywhere. Under the alternative hypotheses, obviously we have inequalities. So, for example, beta 2 does not equal 0, but instead of and, we have or. So the alternative hypothesis corresponding to this null hypothesis would be beta 2 does not equal 0, or beta 3 does not equal 0, or beta 4 does not equal 0, or beta 5 does not equal 0. Why do we have or under the alternative hypothesis when we had and under the null hypothesis? Well, the answer is a joint null hypothesis is a joint restriction, which means that in order for the null hypothesis to be supported by the data or not rejected by it, then we need every element of that null hypothesis to be jointly supported by the data. It would only take one individual element of this joint null hypothesis to be rejected for us to reject the null hypothesis as a whole. So in other words, even if we didn't have any evidence that any of these things were false, okay, so even if we didn't have any evidence that would have led us to reject the null hypothesis that beta 3 is 0, or the null hypothesis that beta 4 is 0, or the null hypothesis that beta 5 equals 0, even if we had evidence against the null hypothesis that the true value of beta 2 is 0, that would usually cause us to reject the null hypothesis as a whole. So it only takes one piece of evidence against the null hypothesis for us to be willing to reject the null hypothesis as a whole. So now we've got the testing framework clear, what I want to do now is to have a look at an example. Oh yes, just before we do that, you can see that the F-testing framework is very much more flexible than the T-testing framework, but it's important to note that there are still certain types of hypotheses which we cannot test in either the T-testing or the F-testing framework. And those types of hypotheses would be any that were nonlinear or multiplicative hypotheses about the parameters. For example, we can't test the null hypothesis that the product of the true values of beta 2 and beta 3 is 2, or we can't test the null hypothesis that the true value of beta 1 squared is 2, and so on. Null hypotheses like that cannot be tested in the classical linear regression model framework. We'd need a more complex non-linear approach, and that would allow us to test such things. Now, we know that if we've got hypotheses involving more than one coefficient, or we've got joint null hypotheses, we know that we can only test those using the F-testing framework. But suppose that we had a very simple null hypothesis that only involved one parameter. For example, the null hypothesis that the true value of beta 2 is a half. Well, you'll remember from previous lectures that we could test that null hypothesis, and we usually would do, using a t-test. So we could do a test of significance or form a confidence interval. But you'll see from what we've just learned that we could also test such a null hypothesis using the F-testing framework. Well, an obvious question to ask is, if we use the two approaches together, will we always get the same answer from both? So if we reject the null hypothesis in the t-testing framework, will we always also reject in the F-testing framework? If we don't reject in the t-testing framework, will we also always not reject in the F-testing framework? Well, fortunately, it turns out that the answer is yes. We'll always reach the same conclusion from the two approaches to testing the hypotheses. And the reason that that is the case is that as with many of these distributions in statistics that are all related to one another, the T and the F distributions have a special relationship between them. More specifically, we can say that the T distribution is a special case of the F distribution. If we take a T-distributed random variable with T minus k degrees of freedom, and we square that random variable, then that random variable will then follow an F distribution with 1 and T minus k degrees of freedom. So you can see that the T distribution is just a special case of the F distribution where the value of the first degree of freedom parameter is 1. So, given that the T distribution is just a special case of the F distribution, whichever approach we used to testing single or null hypotheses, we'd always get the same answer. So it doesn't matter which approach we use. So now, coming back to my example, let's suppose that we have a researcher that wants to test the null hypothesis that the returns on some stock Y show unit sensitivity to two factors, factor x2 and factor x3, among three factors considered. And the regression model is carried out using 144 monthly observations. And therefore the regression is yt equals beta 1 plus beta 2x2t plus beta 3x3t plus beta 4x4t plus ut. We're asked first of all to say what would be the restricted and unrestricted regression models, and secondly, if we've estimated those two models and we have values of the residual sum of squares of 436.1 and 397.2 to perform the test and say whether we reject or not reject the null hypothesis. Well, the first thing that we need to do in this context is to say, well, given the restriction that we want to test, what is the null hypothesis? And therefore, what is the alternative? Well, if we get rid of this model up here for the time being, the null hypothesis that we're testing is that the stock returns show unit sensitivity to the two factors x2 and x3. Unit sensitivity implies that under the null hypothesis, the values of the coefficients for beta 2 and beta 3 will both be unity. So that suggests that the null hypothesis is that the true value of beta 2 is 1 and the true value of beta 3 is 1 at the same time. Just to be clear, what is the alternative hypothesis going to be? Well, it would be that either the true value of beta 2 is not 1 or the true value of beta 3 is not 1. So those are the null and alternative hypotheses. Given that, what are the restricted and unrestricted regression models? Well, first of all, thinking about the unrestricted regression model, again, as previously, the unrestricted regression model will be the one where ordinary least squares is completely free to choose whatever parameter values it likes, and that will be the one that's given in the question. So ordinary least squares can choose the values of beta 1, beta 2, beta 3, and beta 4 in any way that it wants to. What about the restricted regression model? Well, what we do to estimate the restricted regression model is to take this null hypothesis and impose it upon the model. So our model was yt equals beta 1 plus beta 2 x 2t plus beta 3 x 3t plus beta 4 x 4t plus ut. That's our model. If we then impose this null hypothesis on the model, then what will the restricted regression model look like? Well, let's impose this restriction. What do we get? We get yt equals beta 1 plus beta 2 x 2t plus, sorry, that's not right. What do we get? We get yt equals beta 1 plus, well, under the null hypothesis, beta 2 takes a value of 1. So we have 1 multiplied by x 2t. Once again, under the null hypothesis, beta 3 is 1. So we have plus 1 times x 3t plus beta 4 x 4t plus ut. Once again, we know that ordinary least squares, when we use it on a computer, cannot estimate a model of this form where we have a specific parameter here which we're forcing multiplied by the variable. Obviously, because these take on the value of 1, we could just remove those for ease of notation. Once we have that, we know we can't estimate this model in this form on a computer. So this is a restricted regression model, but it's not the one that we actually estimate. Again, if we have a model where we have variables on the right-hand side that have no parameters attached to them, we take those variables over to the left-hand side. So the left-hand side would be yt minus x2t minus x3t equals beta 1 plus beta 4 x 4t plus ut. And finally, we make a substitution. Let's create a new variable called zt, which is yt minus x2t minus x3t. Then the restricted regression model that we actually estimate on the computer will be a regression of zt on a constant and x4t. So you can see one point that I tried to make before. That is, our initial unrestricted regression model had k equals 4 parameters to estimate. We then imposed 2 restrictions on the model, and once we've done that, how many parameters have we got left for ordinary least squares to freely determine? Well, the answer is we've got 2 parameters left here at the end to determine. So we start with 4 parameters in the unrestricted regression model to estimate freely. We impose 2 restrictions, then we get 2 parameters to freely determine at the end. So we've decided what the restricted and unrestricted regressions will be. Now what we need to do is calculate the value of the test statistic so that we can perform the test. So what does the test statistic look like? Well, let's create some space here. The test statistic will obviously be of the standard form that I put up a couple of slides ago. So the F-test statistic is going to equal the restricted residual sum of squares minus the unrestricted residual sum of squares divided by the unrestricted residual sum of squares multiplied by t minus k over m. So all we need to do is to plug the elements into this formula. Well, we're told that the restricted residual sum of squares is 436.1. And we're also told that the unrestricted residual sum of squares is 397.2. Okay, so we then divide by 397.2 there. And it's worth just noting here that once again we know that the F-test statistic can only ever take on positive values. So if you find at the end you've got a negative value for the F-test statistic, almost certainly what you've done is got the restricted and unrestricted residual sums of squares the wrong way round. So then we multiply by t minus k divided by m. What was t? Well, we're told in the question that we have 144 monthly observations, so t is 144. What about k? Remember, k is the number of parameters we're estimating in the unrestricted regression. How many of those were there? Well, there were 4 parameters in the unrestricted regression, and then we divide here by m, which is the number of restrictions. How many restrictions are we imposing on the model? Well, the answer is we're imposing the restriction that beta 2 equals 1 and that beta 3 equals 1. So there are 2 restrictions. And if we calculate the value of that test statistic, it turns out to be 6.86. What we now need is a critical value from the F distribution tables with which to compare that. And we know that what we want to do is to look up the critical value for an F distribution with m and t minus k degrees of freedom. And obviously, in this case, m is 2 and t minus k is what we had on the top here, which is 140. So we want to look up in the F distribution with 2 and 140 degrees of freedom. So if we quickly have a look at the F distribution table, the first thing we note is that it's no longer possible to have different significance levels in different columns all in the same table. All we can do is to fix a significance level, and then every element in the table will correspond to that significance level. The reason that that is the case is obviously that with the t distribution, we had 1 degree of freedom parameter. So each row in the table was a degree of freedom parameter. Each column represented a different significance level. But with the F distribution, we've already, in a sense, used up both the dimensions. We've got 2 degrees of freedom parameter, 1 for the rows and 1 for the columns. So we'll have an F distribution table for a 5% significance level. We'll have to look in another F distribution table for the critical value corresponding to a 1% significance level. So if we just focus on the 5% significance level for now, what is the critical value? Well, we need to look in column M and row t minus k, so column 2 and row 140. Now, unfortunately, in most F distribution tables, there isn't a row 140. So if we look in row corresponding to t minus k is 120, then that's close enough. And it turns out that the critical value at the 5% level is 3.07. Okay, so if we look in column 2 and row 120, the critical value at 5% level is 3.07. What we could also do is to look in another F distribution table for the 1% critical value. And if we did that, we find that the critical value is 4.79 at the 1% level. Okay, so we can see in both cases here the test statistic is much bigger than the critical value, even if we use the fairly strict 1% criterion for rejection. So because the test statistic is bigger than the critical value, the test statistic will lie in the rejection region, and hence we reject the null hypothesis. So we say that we've got strong evidence in our sample to reject the null hypothesis that the true value of beta 2 is 1 and the true value of beta 3 is 1. So that's how we perform F-test statistics. And we could look at many other examples if we wanted to, but they would all work in the same way.